All right, we're live. We're live. We're live. We're live. So today we're going to spend more time on the shortest vector problem. Then we're going to also look at some cryptography in C and C++. We'll read a couple more pages in that book. But today I really want to understand the SVP. So without further ado, I'm going to go ahead and let me get this video here on the Quantum Wallet. Here we go. All right. Share the screen. Share. Cool. We're going to talk about this a little bit here.
Baseball on TBS.
Power
is not.
And at least the L2 norm, the shortest.
Um,
Hello, fellow ANTS participants, and anyone else that might watch. I'm Daniel Martin, and I'm going to talk about two types of lattice reduction problems, a short vector problem and simultaneous approximation. And I'll talk.
just get my notes ready here. All right.
Talk about the idea behind the paper I'm presenting, which is basically that the two are equivalent. So here's some informal definitions for these problems. A short vector problem, you start with a set of vectors and you're asked to find a short non-zero integer combination.
Right.
In other words, you'd like a short element of the lattice generate the original input vectors. So this is commonly called SVP or approx SVP if you don't insist that your output vector is an actual shortest vector of the lattice. And as an example here, there are three-dimensional vectors, and we'd like to know what integers we could put in place of the red question marks to make the output short in whatever.
So it's just saying we have x1, 64, 218, 133 plus x2. Okay, so this looks like a pretty straightforward linear algebra problem. Well, actually, not really. Let's just look at this. So we take one copy. So we take one. So let's think about which combo of vectors would produce such a small output. Well, I'm thinking the first question marker, I'm going to say x1 is this. So yeah, let's say x1 is 1. x2 is... No, actually. I'm going to say that.
Your norm of choices. And in at least the L2 norm, the shortest vector or a shortest vector is 1, 3, -1, and those are the integers that you would need to get it. Simultaneous approximation problem starts with just one vector, and we're asked to find a multiple that's near an integer point, meaning all of its coordinates, the output coordinates, are close to integers. So here's an example, another three-dimensional vector. What integer could we put in place of the red question mark? If you use 106, you see in the output there that
Okay. So it says the shortest vector here is 1, 3, -1. Let's do the other example. So simultaneous. So I'll just label this approximation example. which is the formal definition. Informal definition is given a vector, find integer closest to integer. -3, 5. He also uses 15/51 and pi. And he says, what value of x? Okay.
Could be put in place of the red question mark. If you use 106, you see in the output there that each of them is 1 or 2 hundredths away from the nearest integer. So it turns out for a vector like this that has irrational entries, there's no limit to how close you could get to an integer point and still not land on it. So it's pretty common to bound the multiple that you might take. So if our bound was, say, 200, then 106 would be a great choice. Or alternatively, if the input vector is rational, then another possibility would just be to exclude the trivial solution, multiples of the least common denominator. All right, so here's a brief history of the subject. We should probably start with the Euclidean algorithm, but
there's no way
that would skew the timeline in an unattractive way. So we'll start with Lagrange Gauss in 1773 or around then, solving the lattice reduction problem in 2 dimensions. And I'll mention what I mean on the next slide, what it looks like to solve lattice reduction. Then in 1842, Dirichlet began the study of lattice reduction in arbitrary dimensions. What that means is the L paper.
Excuse me, sir, would you like to earn income while you learn how to code?
Yeah, tell me more about that.
DevSlopes helps you earn income while learning how to code by helping you acquire paid freelance work.
Could
be used to in cryptography. They built a crypto system based on its assumed hardness, and that's helped to popularize the study of the subject. And then just last year, Agrawal, he's the A in the AKS primality test, gave the reverse of the Lagrange reduction, showed how short vector problems could be solved with a simultaneous approximation oracle. And we're going to give an outline of a different technique than his, but I'll reference the 2020.
Okay, perfect.
Okay. So here's an overview of what we're going to try to do. So basically, in lattice reduction, we're starting with a bad basis, and we'd like to get a good one. So what I mean by bad basis, visually, the vectors are far from orthogonal, but what makes it bad? Well, one thing that you might want to do with a lattice, one thing that's often done, is you use your lattice points to approximate things that are not in the lattice. So in this case, 11.6, 4.2.
Sorry, for some reason, hand feels weird. It's kind of hard to write, but that's fine.
Denoted there with lattice. One thing that's often done is you use your lattice points to approximate things. With a lattice, one thing that's often done is you use your lattice points to approximate things that are not in the lattice. So in this case, 11.6, 4.2, denoted there with a purple triangle. I'd like to find an element of this lattice generated by the blue and red vectors that's close to it. So here's what I mean. Here's, for example, 1 blue minus a red. We're sort of zigzagging our way over there. We won't try and get there that way. That might take a while. So instead, let's try and actually solve this equation in the top left. Question mark, question.
So once again, we're just going to draw this out in terms of both basis vectors. So 6, 14. So 6, 14 is up here. And then 3, 8. Is right there. So I guess we can kind of draw this. So he chooses to draw this out with 2 different lines that stem from the origin. So lattice reduction.
is you use your lattice points to approximate things that are not in the lattice. So in this case, 11.6, 4.2, denoted there with a purple triangle. I'd like to find an element of this lattice generated by the blue and red vectors that's close to it. So here's what I mean. Here's, for example, one blue minus a red. We're sort of zigzagging our way over there. We won't try and get there that way. That might take a while. So instead, let's try and actually solve this equation in the top left. Question.
So I guess it's just saying you have a lattice base. And you want to approximate going to that. You want to approximate. Yeah, it's just saying you want to approximate some lattice point or some non-lattice point with your lattice point. So in this case, you can draw 11.6 out just like he drew it here. 11.6 comma 4.2 is somewhere right there. Then he says, so now we have 6, 14, 3, 8. Yeah, I think this works.
Question mark should roughly be equal to that matrix product. So we can do that multiplication. We get out 13.4 negative 22.9. That's what we'd like to put in there. But remember, for a lattice, these have to be integers. So right. At least my best guess would be 13 negative 23, rounding each one to the nearest integer.
Huh. And this works, you have to recall, guys, this works because I'm not mistaken. There is a unimodular matrix. We just did this in day 2. We talked about how a lattice basis is not unique, and it's not unique because they're a unimodular matrix. And I believe that's why this works, because unimodular matrices have a property where their inverses always work out. They always have an inverse, meaning you can always compute an inverse, which is what I think we're able to do here, right? We're able to compute the inverse and then say this is just equal to some 13.4 negative 22.9, which is approximated because, so if I'm not mistaken, here's what we're going to matrix inverse calculator. And I actually want to see if this lattice basis or if this lattice basis or this basis gives us, oh my gosh, what is it? What are we doing here? There we go. I want to see if we get, so if it is unimodular, this inverse should be, oops, I need to share this tab instead. So if this one is in fact, so if it is a basis or if it is a lattice basis, this should be an integer result. So let's just check right now. It's not, and that's interesting. So I guess we can't apply the same. I guess that means that we can't really apply that same reasoning. So I guess it's not unimodular then. I don't know. Wait, no, I thought it would be. Let me go back. A lattice always has a basis. The basis is not unique. Oh, I'm dumb. No, it's not unimodular. I'm really dumb actually, because I'm really dumb actually. Wow, I'm pretty stupid because it's unimodular only if the determinant we just said is 1 or negative 1. So in this case, this is 48 minus 42. That's not a determinant. That's good. Or approximately 13. So yeah, all he's doing here is just taking a lattice basis He's using these basis vectors of a lattice, picking an arbitrary point on that lattice, or picking an arbitrary point not on the lattice, and then finding how many multiples you need to scale to that point with the lattice, with the approximate. Oh, this makes sense. Because it's not on the lattice. If it were on the lattice, if this were on the lattice, I'm willing to bet. Yeah. Okay, now I get it. If this point were on the lattice, these values wouldn't round. We get an exact number, but because, yeah, sorry, that I was thinking. Let's write that down. This point. Huh. Takes me a while to, I guess, work out the matrix math here. Yeah, I don't see these things first try, so I need like always have to. Yeah, so then once you have that, okay, that's cool. So then once you have that point, then you go back to the original lattice and then um, call for cool. That's really interesting.
We see that our best choice,
Yeah,
we can multiply 12,4 by the inverse of that original matrix.
really cool.
You see that we should have taken, instead of 13, negative 23, we should have taken 14 copies of the blue vector and negative 24 copies of the red vector. But how could you have predicted that? How could you have predicted which way to round? And in general, even if you did know,
Ah, I see. So it really is just a rounding thing. Here, at least, this part makes sense. Because if you remember back to when we just worked out, how many methods we need, and we rounded to the nearest. So when we looked at 11.6 and 4.2, what we did essentially is we computed the inverse of the basis, multiplied them out, and then we had 13.4 and negative 22.9. And the way we did it, we just rounded to the nearest. So 13.4, we said it would round to 13, and then 22.9 would round to 23, or sorry, negative 22.9 round to negative 23. But as we just worked out, this is not the best answer. We just proved that if we use those points, we end up landing at a point 9 comma negative 2, which isn't right. But then we see from a practical standpoint how we had chosen 14 and negative 24 as our rounding, as our way to round our approximation. We would have gotten plus 6, so we would have landed from 9 comma negative 2. We would have now landed at what? We would have landed at 12 comma negative 4. But of course, we didn't know that because there's no way he said
that rounding up or down would give you the right coefficient. You can see that in n dimensions, you already have an exponential number of choices, 2 to the n. So this problem gets hard as the dimension increases. You can also see from this example why something like this, why this problem might be useful in cryptography. If you and I wanted, say you wanted to send me a secret over the internet, if I have this great basis for the lattice 3002, I could make publicly available this bad basis 61438, which describes the exact same lattice. You want to send me a secret, you could encode it as an integer pair. In this case, send me a secret. I could make publicly available this, cryptography. If you and I wanted, say you wanted to send me a secret over the internet, if I have this great basis for the lattice 3002, I could make publicly available this bad basis 61438, which describes the exact same lattice. You want to send me a secret, you could encode it as an integer pair. In this case, 14 negative 24. Multiply 14 negative 24 by this public bad basis, and you get out 12 comma 4, this little green dot. Don't share the green dot because then people could multiply by the inverse of that bad basis and figure out 14 negative 24. Just perturb it ever so slightly so that I, with my good basis, can very quickly find out what the nearest lattice point is and get out your secret, while other people with this bad basis, unless they have a good lattice reduction algorithm, can't figure out your secret. This little green dot. Don't pull this bad basis 614. If I have this great basis for the lattice 3002, I could make publicly available this bad basis 614. 38, which describes the exact same lattice.
I see. So what I don't understand is how do we know when two bases correspond to the same lattice? So I know this for sure corresponds to the idea of a unimodular matrix. Yeah, a unimodular matrix that generates B1 equals B1 times U. So I guess we can work this out really quickly as an example. Also, by the way, this example is so much more helpful than the textbook or the book that we're going through right now. This is it's like practical almost. So let's look at an example. So let's just say, so we have lattice basis number 1, 3, 0, 0, 2, and we said this is equal to the other way around, so it's a little easier for our calculate. 6, 3, 14, 8 is equal to 3, 0, 0, 2 times some 2 by 2 matrix that will result in this. So, this matrix has to be unimodular, right? 3. So this has to be 2 right here. This has to be a 2, right? Because we need 2 copies of this. This needs to be. So I'm just working through. Yeah, I'm just working through like the math, I guess, trying to prove that the matrix that binds both these bases together is in fact unimodular. It's a simple algorithm, I think. You just need to work through each of the. It's just systems of linear equations. So here we have 0, 6. So we should almost take 1/2 here. Does that work? Oh wait, whoops, sorry. It should be 1, not 1/2. So we have 2, 1. This is right. 1. Yep, that's right. And then we need 14. So it should be a 7. And then 8. We should get 4 here. So this right here is our unimodular matrix. So we just found that our unimodular matrix is in fact cool, and that's actually really easy to find. You get a system of linear equations, and then we can check right now. The determinant is 8. So yeah, these 2 bases do span the same lattice, and we just proved that right here. So now we can say, because there is a unimodular matrix that binds both basis vectors together, both of these bases talk about the same lattice. So let's go on.
You wanted to send me a secret over the internet. If I have this great basis for the lattice 3002, I could make publicly available this bad basis 61438, which describes the exact same lattice. You want to send me a secret, you could encode it as an integer pair, in this case 14 negative 24. Secret, you could encode it as an integer pair, in this case 14 negative 24.
14 negative 24. Let me. I don't know. I still don't really know what that means.
Basis 61438, which describes the exact same lattice. You want to send me a secret, you could encode it as an integer pair, in this case 14 negative 24. Multiply 14 negative 24 by this, and you get out 12, 4 green dot. Don't share the green dot, because then people could multiply by the out 12, 4, this little green dot. And you get send me a secret, you could encode it as an integer pair, in this case 14 negative 24. multiply 14 negative 24 by this public bad basis, and you get out 12 comma 4, this little green dot. Don't share the green dot because then people could multiply by the inverse of that bad basis and figure out 14 negative 24. Just perturb it ever so slightly so that I, with my good basis, can very quickly find out what the nearest lattice point is and get out your secret, while other people with this badly, so that I basis and figure out 14 negative 24. Just perturb it ever so slightly. Don't share the green dot because then people could multiply by the inverse of that bad basis and 24 by this public bad basis, and you get out 12 comma 4, this little green dot. Don't share the green dot because then people could multiply by the inverse of that bad basis and figure out 14 negative 24. Just perturb it ever so slightly so that I, with my good basis, can very quickly find out what the nearest lattice point is and get out your secret, while other people with this bad basis, unless they have a good lattice reduction algorithm, can't figure out your secret. So in this case, this is an example of using what's called the closest specter problem.
If you wear glasses or contacts, I have a bit of bad news for you. Life with glasses and contacts is always fun.
Wonderful. Tweak it a little bit.
While other people with this bad basis, unless they have a good lattice reduction algorithm, can't figure out your secret. Well, this can very quickly find out what the nearest slightly, so that I, with my good basis, can very quickly find out what the nearest lattice point is and get out your secret, while other people with this bad basis, unless they have a good lattice reduction algorithm, can't figure out your secret. So in this case, this is an example of using what's called the closest specter problem. And it doesn't in any way represent or closely mirror today's lattice reduction uses in cryptography. But again, at the end, I'll give a reference to Regev's LWE if you're interested in how lattice reduction is used in cryptography. All right, so now I'm going to go back to our two original problems, and I'm going to talk about what separates them, and that'll give us an idea of how to reduce from one to the other.
Wait, it was not you?
But again, at the end, I'll give a reference to of using what's called the closest specter problem. And it doesn't in any way represent or closely mirror today's lattice reduction uses in cryptography. But again, at the end, I'll give a reference to Regev's LWE if you're interested in how lattice reduction is used in cryptography. All right, so now I'm going to go back to our two original problems, and I'm going to talk about what separates them, and that'll give us an idea of how to reduce from one to the other. So both of these matrices have the same determinant, 5 cubed, but one of them is very special. It's the one on the right. The one on the left, actually, the first 3 rows were generated randomly, and then the last row I computed in order to give a determinant of 5 cubed. But since the first 3 rows are computed randomly, you might expect that just because the determinant of the whole matrix is 5 cubed, just because it doesn't have full rank mod 5, that doesn't mean that its 3 by 3 minors don't have full rank. And since they're computed randomly, they probably don't. And in this case, that's true. The top left 3 by 3 minor, for example, has determinant not divisible by 5. So this matrix has rank 3. Modulo 5 over F5, the field of 5 elements. And that's not the only 3 by 3 minor you could have taken. Here's another one. So you could have used the first, third, and fourth columns, and that would have given you full rank over F5. And I say that's typical because, again, the full determinant being divisible by 5 doesn't imply anything about its principal minors. As you could guess, that's not true of the one on the right. This is the matrix that I've chosen so that each of its 3 by 3 minors is divisible by 5. It doesn't matter which ones you take. And actually, the situation is worse here. This matrix is chosen so that each of its 2 by 2 minors is even divisible by 5. So this doesn't even have rank 2 mod 5. This matrix only has rank 1. So you could take any of these, none of these vectors are 0 mod 5. So you could take any of the 4 vectors that you see as your one generator over F5. So I took the first one and I called that X. Another way of saying that would be over the integers, which is, the lattice that we care about. Over the integers, this is generated by X and 5 times the standard ordered basis. So you might recognize that as very similar to a simultaneous approximation problem. In this case, a pretty easy simultaneous approximation problem. You could just reduce X modulo 5 and see that a shortest vector in this case is -2, -2, -1, 1. But it doesn't look exactly like simultaneous approximation, because remember, we wanted to find a multiple that put us near an integer point, and this is finding a multiple of x that puts us near 5 times an integer point. But that's okay, just scale everything by 5. It doesn't change the shape of the lattice at all. So we could solve this problem instead, taking multiples of x over 5 and finding what puts it near to something in z to the 4th, an integer point. So this is a simultaneous approximation problem. And you can see what makes it unique. It has rank 1 over whatever that number is, in this case 5. Here's what it looks like visually. On the previous slide, this D that's labeled in each of the scaled standard ordered bases, this D was 5 on the previous slide, and here's X. So if we want to see what the full lattice looks like, we take multiples of X and we reduce it modulo D. So here's twice X shifted back to be in the cube, and here's 3 times X shifted back, and we keep doing this until we don't get anything new. And here's our lattice. It includes the blue points. Well, if we wanted to draw the full lattice, we would then tile this cube over all of 3 space, and that would show us the full lattice. Okay, so this is generated by x and dz cubed, or as we said, if you scale everything down by d, divide everything by d, you have a simultaneous approximation problem. But this is a very special case. Most lattices that have determinant divisible by d wouldn't have rank 1 mod d. Most of them would have some other vector. So let's say we have a more general lattice reduction problem. So here I've thrown in an extra generator, y, and this would generate, I don't know, 40 or so more. Shift all of this. Scale this down by d, C3 lattice reduction problem. The 4th, I'll say.
Yeah, I don't think that's not very useful anymore. All right, cool. But that was cool. It was a cool video to watch. Let's go back to the GitHub. Let me see something really quick. Let's just see. We stopped here. Short of the problem. I don't know if I want to do Gram-Schmidt. Oh, cool. You can find that, huh? Okay. We'll get back into this math later. We're going to shift focus and we're going to shift towards cryptography in C. So this is more of an implementation than, yeah, let's go over to the implementation of some of these. And I was doing this a while ago, and I took a break to do this. I want to get back to this. I stopped on, I believe it was a little bit earlier. I stopped at the 2. Yeah, right here. Whew. So to recap, this is actually a really interesting book so far. I went to the first couple of chapters, the first 2 chapters. Let's talk about what we have found so far. So the chapter 1 just talks about cryptography requires the study of natural numbers. So you have discrete theorems, successors of 2 natural numbers are unequal. For every natural number, there's a predecessor, and then you can do a complete induction to prove this. We did that. It's pretty easy, and we just proved that induction also gives us arithmetic operations on the set of natural numbers, as well as exponentiation and multiplication. Chapter 2 is when we start talking about the actual implementation of this, like in C, or I guess like the early ones. So the first thing is, of course, you have to store large numbers in C. And by large numbers, I mean the numbers that are hundreds of digits, which are far beyond any primitive type that you'll be able to access. The largest number you can access in C is an unsigned long. Primitive type is an unsigned long. That'll give you range. What is the range of that? I know a log is or 8 bytes, right? So 2 to the 64 minus 1 possible. Is that right? Yeah, that's right. 2 to the 64 minus 1 is your maximum value. And C, it's an unsigned long. So we talked about, I guess, how to store these large numbers, and the way we're gonna do it, the way the book recommends doing it, is use vectors with a standard data type. So once again, unsigned longs are preferred. And we're going to use unsigned shorts because the product of two unsigned shorts is always less than or equal to the product, or always less than or equal to an unsigned long. So in that case, we talked about how. So now we talked about that, how we're going to actually store these digits in an unsigned short. Because you have, let's say you have 100 unsigned shorts corresponding to one number, right? Sorry, that's a little bit too much. Let's say, because then like a short is what? 4 bytes? Meaning you have 32 possible digits to put in. Right? You have 4 bytes, you have 32 bits, which all correspond to 32 digits. So if I wanted to pick a number with 200 digits, I'm going to have what? 200 divided by 32 plus 1 shorts. Now the question is, how do we store digits in an unsigned short, right? Should we store digits from largest to the smallest digit or smallest to largest? It's very interesting because there's actually a very clear winner, which one should work. And the clear winner is we should store numbers with Little Indian notation. So if you're not familiar with Little Indian notation, it just means you store the least significant digit first. So if a number is 1,000, if a number is 10,002, the first number I'll store in memory is 2. The reason why, this is actually a pretty cool reason actually. So it's a really cool reason actually, and one that I kind of want to show because it's really interesting. So let me go ahead and we're gonna open up. So let's talk about why there's a clear winner. It's pretty cool. So suppose I had a number. Let's say 101012 Let's say it goes on for hundreds of digits. Actually, no. Let's just say, just assume this is the end of a really big number. Okay. So on version number 1, oh, what the? How do I get my? Where's my pen? It's so silly. Where is my pen? Okay, I'm gonna just reload the slide. Okay, sorry. So if I have my really arbitrarily big numbers, but suppose this is the end of an arbitrarily big number. Way one, if I store this in memory. So here's my memory. We're gonna call this address what is it? So we're just gonna know this is the first address. This is like our last address, whatever. Some number. This is some number as well. I'm making this up. I'm just trying to show that this is our 2 addresses. So the first thing is we have to store the size of this. Our first variable should be storing the size of this. That's a given. So our first bit will always correspond to the size of the number because we need to specify how many digits we are going to add, so we know where to stop and where to start. So let's say I do 5, and let's just say the first implementation. Let's say we store it like this. So our numbers will be stored like this. Each corresponds to one byte. Oh, I'm sorry. Each short is 4 digits. I lied. Each is 4 digits, not 32 bytes. What am I talking about? It's 4 digits. This is 2 shorts right here. Anyways, what if I wanted to add? Let's say I wanted to add 2,000, which is very reasonable. In cryptography, you're going to add and multiply these very big numbers. What will happen? So now if I add 2,000 to this, or even better, let's say I'm going to add 120,000, right? what will happen? So I'll still have my 5 here, 0x0, 0xf, whatever. This is just like pointers, I guess. Not pointers, this is just like placeholders. What will happen here is this new digit will now be 1. This one will now be 2, right? And then we would have to continue and do 1. Wait, whoops. What the fuck? I'm so stupid. I missed it a little bit. But here, look, this is better. Sorry about that. 1, 1, 1. Oh my gosh, I'm so tired, y'all. I'm so sorry about that. Point is, let's just add it up. Sorry, I'm kind of bullshitting here. 1 should be a 2, you dumbass. You did not. Oh my, it's not even 2. It's 3. I'm losing my shit. I'm losing it. Because the answer for this is 1, 3, 0, 1, 2, 3. There we go. Oh my gosh, I'm so sorry. I don't know why I had to. I'm not very smart today. Anywho, point is, check this out. From here to here, what did I have to do? I had to add this arbitrary large number. I had to. So in memory, let's note this as 1, 2, 3, 4, 5. If you notice, in our new system, 3, 4, 5, 6, I had to shift all of these numbers compared to here. So I had to really change 1, 2, 3, 4, 5. So now I have to perform 5 operations behind the scenes to get my memory that way. Right, which is a really big deal because if you wanted to add a really big number or subtract a really big number, you would have to change 5 parts of your memory, right? You have to modify 5 different parts in your memory, which is a problem. Now, let's store this little Indian notation. We would have 3, 2, 1, 0, 1. Now, what if I add 120,000? 3 would stay the same, 2 the same, 1 the same, 0 the same. Only here would I have started to modify my values, and so now I'd put 3 here, 1 here. So you can clearly see from here to here, same, 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 same. We only had to modify 2 values versus 5 values. So there's a clear winner. When you add and multiply big numbers, you save up so much time and so much space by doing the second approach, storing in Little Indian. Therefore, we're doing it in Little Indian. So the representation of large numbers. So everybody just clear this. Do I have to like view image, clear image? There's a clear winner. Now I want to talk briefly about. Let's talk briefly about. So now we can say the representation of large numbers has this formula, and this formula we see is going to be. So the representation, or this is my Compark. I'm going to abbreviate as large number. This representation is now going to be in memory. It's going to look something like length. It'll look something like this. We'll store the length of the number first, and then we'll store n1, n2, all the way up to nn, where L is the length of our number, and each of these are digits. So we actually, this shouldn't be, I'm going to be exact. This is going to be NL, or N is the length of the digit. So pretty cool stuff. And we can see here, so the value, the way we would calculate the value, we'd say we have a summation from I1, and we're going to end at the first element, right? Because the first element is just the length. And we're just going to calculate, we're going to get the current number there, multiply it by whatever the base is, I minus 1, right? Because we're stored in Little Indian. And this only works if n is greater than 0. And of course, 0 if the length is 0, we have no number. Right? So it's pretty cool stuff. Pretty cool. So yeah, so our most significant digit is what? It's a test question. And yes. Right? It's just saying right here, the length, least significant digit will always be what? Yes, very good. Cool. So that's how we talked about that. And then we said we can call this a Clint object. That's what the book calls it. This stands for C representation of large integers. Yep. Where we talk about that. And then, so it's pretty cool. And Clint objects, once again, we're not unsigned. The Clint objects are always going to be unsigned. Yeah. So our max digits will just be max digit plus 1. And we talked about how Clint objects will have the range 0 to whatever your base is times the max b, or I said max b is, that's the only possibility we have, or max b is, what is max b? We said this was the maximum number of shorts. So it's max digits plus 1, or max shorts in Clint object. Great. So we defined what a Clint object is. We discussed how we lay it out. So now we've talked about representations, values, as well as ranges and basic implementation of the max digit. So it's pretty cool. Yeah. And it's cool. In the code that he has written, he said max digit on the code that was written. I went through this because I was curious. He said it equal to 256. So if we take that number, we talk about this. We can clearly see that. So how the book's organized, the book is claiming that each short is 1 digit. So what, a short is 4 bytes? No, sorry. Oh my God, I'm so stupid. A short is 2 bytes. A short is 2 bytes. And he says each short corresponds to 1 digit. That's what the author chose to implement as. So we can say this is, so like, for example, like a number that will take up the most digits, you would have, then you would also have digit 0 all the way up to digit 255. This is equal to 257. I'm gonna say memory slots, but this is a placeholder. The whole point of this is just to show that this is also equal to our max b right here. This is how he got that. Equals. So to be fair, the reason why I see this working is because the thing we'll call it padding. So if you pad to a short, because the issue with this is that, so the issue with just putting your numbers willy-nilly in memory is that if you have like what, let's say we have size 10 and then we have what, like a couple of digits, whatever, a couple more digits. The problem is if you don't pad to anything, what if the next number is what, size 7? How would you know when to stop? So that's why we take each of these and place into a short. Instead of just because we very easy just said this, oh, just make this a character, or yeah, make it a character. Is 1 byte. You could represent plenty of numbers with just 1 byte. Definitely a 1 digit is one character is more than enough to show that way, and each of these are also a short. But the way he's doing it here is just because you would pad to the short, next digit, pad to the short, right? So I don't know. That's my guess why, but I'm not too sure. Yeah. And then, so last thing we specified was the maximum. Oh, that color is horrible. The maximum bits or the maximum addressable bits is pretty easy. You just take the max digit, left shift by 4, which is the equivalent of saying 2 to the 4 times 256, which is what, 16 to 56 is 4,096. It's just the power of 2. So 496. So we can say this is the max addressable memory. And the reason is this is what corresponds to how many shorts. You just divide this. So this is 512 bytes, which is also the same as 256 shorts, which makes sense because in a number that's 257, as we said here, you only want to modify these values. You don't really care about this L value because you're not looking to modify it. So it's pretty cool. And then, of course, the last thing I'm going to mention here is if you want numbers that are bigger, you would define he defined it as Clint double, and you just take 1 plus max digit, and you left shift 1. It's the same as, or this is the same as multiplying by 2. Clint Q. If you were to guess, max digit shift 2, because that's the same as multiplying by 4. So this is the you would like define these as such if you wanted to get more digits, but I don't know if we're going to. Yeah, so that's kind of the basics. That's what we talked about. I want to use this, and let's start talking about adding and subtracting these numbers. Okay, interface semantics. Oh wait, I don't think this is as important. If I'm not mistaken, I don't think this is important. This just means overflow, underflow. I did comp park, so this part makes sense to me. All right. Fundamental operations. All right, let's talk about addition and subtraction in this representation format. So it's pretty cool because this is pretty cool. This is a lot of Compark stuff. We did this in Compark like 2 weeks ago. Like all this stuff. Of course, we did it with binary. We didn't do it with like these kind of formats. So this is pretty cool, I guess, to just look through. Okay, so the principle of operation with different signs, underlying algorithms equivalents. We can deal with them together in this section. We consider operands and Boolean representations. Okay, well, this is not Little Indian. This is, I think, just okay, this looks pretty hard, actually. So this is like, so here we're assuming that, okay. So in this case, it's like Little Indian. So just take the number 1034 plus. It says you can assume A is greater than or equal to B. Okay, so this is a plus 1025. This is we'll label this as Big Indian because for whatever reason he's choosing to give this example in Big Indian. So let's write out the algorithm for addition. I equals 0, C equals 0. T equals plus BI plus C SI equals T mod B, and then C equals round down okay. I think what I'm gonna do is I'm just going to here's what I'm gonna do. I'm gonna get a picture of this algorithm, import it into here. I'm just gonna worry about the example. We're just worry about working through an example to, I guess, kind of show this. And I'll show this with A plus B with the example, the numbers that I have here. So let's just crop this out. Crop. All right. All right, let's put it up there. All right. Now let's actually work through this. Okay. So we're gonna have an I variable, C variable, a T variable, and S. So we're going to separate this into 4 different categories. Okay. I equals 0, C equals 0. Set T equals AI plus BI. So 4 plus 9 is just 9. That's our T. Plus C. Okay. S of I or S of 0 is equal to T. So I recall that our B is equal to 10. We're working in base 10. Actually, you know what? Let's do an example where we don't. Let's work in base 5. No. No, let's just do base 10 for now. And I'm going to modify my example. I'm going to get some carries in here. So we're going to do 1037 plus 1025. That's smart. So T is 12, actually, in the first iteration. We'll do S of I, so S of 0. Two. And now C is 12 divided by 10. But if I'm not mistaken, when the brackets look like that, what does that look like when the brackets are like down? Floor. Okay. So we have C is equal to 12 divided by 10 is equal to what? Like 1.2 something, but the floor of this is just equal to 1. So C is not equal to 1. Oh, I see. This is pretty cool. It's pretty cool. So it is like you just take it like an adder. Because the way I was taught, I'll do this way first, then I'll talk how I was taught. Set I equals I plus 1 if I is less than what is N? N is 4. So we're going to repeat this. This just repeats. Go to step 2. So T is equal to A1 plus that was 5. Oh, plus the carry is equal to 6 actually. Equal to 6. S1 is equal to, what is T mod B? Is 6 mod 10 was equal to 6. And C is equal to 6 divided by 10 is equal to 0 point something, which will floor to 0. So C is back to 0. That's cool. So that's how they're calculating the carry. So I'll talk about how we do it in Compark. And I'm going to repeat. I equals 3. I equals 2. I equals 2. T is 0. S of 2 is equal to 0. And then C is equal to 0 divided by 0 floors is 0. I equals 3. And then this is our last case for I. I equals 3. We're going to do T equals 2 plus 0. T is not equal to 2. And then 2 mod 10 is equal to 2. So we have 2. S of 3 is equal to 2. And now C is equal to 2 divided by 10 floor, which is equal to back to 0. So that carry. So that's cool how they're calculating the carry. They're just taking the floor. That's interesting. I've never seen that approach. So then we're done with the first 3 steps. So we set. So now we do set T equal. Oh, that's weird. Oh, I see. No, this is okay. No. So this is fine. This works. So the output is just 2062, which we found is right. Of course, when the numbers are different, you have to do it a little bit differently. But here's how we did it in ComPark. We treat it as like a vector. So we would just do 7 plus 2 is 12. So it's 12 mod 10 is greater than 1, which is greater than 0, which it is. You take the carry, you add a 1 there, 4, 6, 0, 2. So the whole point was you create like almost like an adder, but I guess that's what we're doing here too. It's very similar. It's not too far off from what we already have here. Cool. I wonder what to do another example of this, but I think for now we're good. I might come back to this later today, but this is a good session. Just we I guess looked at a general purpose algorithm to add. We'll look into. We did more shortest vector problem stuff. Oh, sorry, we did closest vector today. This was closest vector. Yeah, just to recap. You take two basis vectors that span the same that create the same lattice. One of them is a good basis, one of them is a bad, and your good and bad is all relative, but a good basis will a bad basis will be closer, be further away from the point you're trying to find, which is a non-lattice point. The good basis will be closer, and then you just use those 2 points. Yeah, and as you use those 2 points, you make the bad basis vectors for that same lattice. The public key, and you encode it with an integer pair. Keep it secret. And yeah, it's pretty cool stuff. Yeah, we'll get back to this in a minute. I don't want to, because I do have more stuff I need to do today, but I wanted to get a brief session in on this Friday night, just because. Why not? It's a cool project. So see everyone later. Take care.